Anyone can build a box that holds water. But how do you hold 9 tons of it? 6 meters in the air? And without it crashing down? Hello, my name is Universiti BMM1213 with metric number KA24161, and today our group will text you on the physics of this beast.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hamza Perwira bin Masri. My number matrix is KA25099. So now I will explain about the centroid analysis. So the system was divided into two parts, which is the tank and the frame support, which the tank is modeled as 2 times 2 times 2 meter cube, while the frame support has 6 meter height and divided into 4 column steel structure. The coordinate system uses vertically y-axis, measure upward from the ground, while x and z axis lie on the horizontal plane. In this calculation, we use the unit of the meter. So due to the geometric symmetrical, the centroid of the x and z coincide with the geometric center of the structure. Therefore, we consider only y-axis to calculate the centroid. We can use this formula to find the centroid. Assuming equal mass distribution, its centroid is situated at its geometric center. So, based on the information that we have, we can calculate the centroid. To conclude that the vertical reference axis, which is the y-axis, we measured from the ground. The analysis show that the filling tanks raises the center of the gravity. So this raises, giving impact on the structure, which is make it more top heavy and giving impact on the stability of the structure. That's all from me. Thank you very much.
What happens to a structure when its heart moves nearly 2 meters towards the sky? Have you wondered? Hi, my name is Nurfatin Shahira binti Yusman and my matrix number is KA24155. Most people see a water tank as a static object, but as engineers, we see it as a dynamic shift in power. When we add 8,000 kilos of water, the center of gravity climbs from 5 meter to a critical 6 meter. How do we ensure that a 10 kilos of top-heavy giant doesn't tip under the pressure of the wind? This audit reveals the mathematical shield, the X bracing, that keeps this tower standing. Now, let's continue to the technical breakdown. So first we have the critical load. Our total system weight, the W total, reaches 88.3 kN, factoring in both the galvanized steel and the full 8,000 kilograms of water capacity. And then we have the centroid paradox. In its empty state, the structure is stable with a centroid at 5 meter. However, filling the tank creates a top-heavy profile as the centroid shifts upward by 1.6 meter. Next, we have the force distribution. So, using rigid body equilibrium, sum of Fy equals to 0, we have confirmed that the 83.3 kN load is distributed perfectly across the 4-column frame. For column integrity, each individual leg provides an upward reaction force of 22.1 kN. So, for the conclusion, why 13.57 meters? So, the analysis concludes that while the upward shift in gravity drastically reduces natural stability against lateral forces, the engineering design compensates for this through two key factors. The first one is the geometric shield, the X bracing. Because a simple 4-leg frame is structurally intermediate and unstable under side loads, the X bracing is the primary defense.
We proved that the steel legs can hold the weight the best. However, there is a greatest enemy here, which is the gravity, and the worst enemy is the wind. So whenever the wind is passing through the structurally squared frame of the steel legs, it can make it collapse and fold like a cardboard box. Therefore, that is called as a racking in engineering term. And that's why we have implemented the X braces, which acts as a triangle shape. As we all know, triangle is one of the greatest and structurally strongest shape. That's why we have implemented that to maximize and hold the potential energy of 10,000 kgs weight of the tank.
So, does it safe? Our group calculations prove a safety factor of 13.57. We designed it for wind, for rust, and even for mistake. And science says safe. Thank you for watching our video.